So they get started. Okay, it's time. Well, today we have a special speaker, Professor Ibrahim Abdulhalim of Ben Gurion University. And let me give you a brief information about him and his research. Professor Abdulhalim is with Electro-Optics and Photonics Engineering Unit, ECE School of ECE School at Ben Gurion University, Israel, since 2005. He worked in academic institutions and companies such as OCSC in the University of Colorado at Boulder, and the ORC at Southampton University in England, that I'm guessing, and the Tin Film Center of the University of Western Scotland in KLA, Tankor, NOVA Measuring Instruments, and GWS Photonics. His research activities involve plasmonics and photonics biosensors, liquid crystal devices for imaging and energy saving, biomedical imaging, optical metrology, and energy devices. And he published over 300 articles, 2 books, 12 chapters, and inventor on 22 patents. He is a fellow of IOP and SPEI, and an associate editor for Journal of Nanophotonics, for journals of sensors and biosensors. He founded 2 companies and specializing in developing miniaturing plasmonic and photonics biosensors and liquid crystal devices for photonics applications. As you see, he is a photonics, a true photonics guy, and he's going to talk about the miniaturized photonic devices for biomedical, agriculture, and environmental applications. Please welcome him.
Good morning. Most good afternoon. Thank you very much, Mustafa, for the invitation. Thanks for your opportunity. My name is Ibrahim Abdulhalim, and I work on a variety of things, starting from this.
Yemek veren hastamını yakırsan yemek yiyelim. Tamam abi. Tamam.
Yeah, maybe you can go back one. Yeah. So usually I start by thanking all my collaborators. There are many of them from different countries, and also from same university, in Gurion University, and students, of course, and postdocs who are doing the work. I work, as mentioned, yeah, thank you. Oh, okay. So I work on a variety of things, actually, in devices, methods, and we incorporate materials, of course, and biosensors. So in terms of devices, we work with liquid crystal devices, such as tunable filters used for spectroscopic imaging, polarization control devices, for polarimetric imaging, spatial light modulators, tunable lenses, and lately also smart windows. We incorporate them into imaging systems, and we develop applications. The biosensors part is also related somehow to optical imaging. And here we focused mainly on plasmonics, both the what's called the classical plasmonic sensors, the extended SPR or nanoplasmonic ones. And You work with the surface enhanced spectroscopy as well, Raman and fluorescence. So here is a selection of things, maybe supposed to be a video here, which I will show also. Much mentioned by yeah. Okay. No resolution, but okay. So these are part of the things that I work with. This one, I arrived to a position where I create two companies. One is producing this miniature SPR biosensor. The other one is related more to liquid crystal devices. So let's start with the plasmonic sensor. Now we know that there are two types of plasmons, the extended one, which can be excited on the interface between semi-infinite metal and the dielectric medium. And the second one is on the surface of nanoparticles or nanostructures. And they both have advantages and disadvantages depending on the applications. But the main issue is that this one is very well pronounced as very high sensitive refractive index sensor. If you think about spectral sensitivity, is like few thousands, sometimes few tens of thousands of nanometers per RIU, as compared to the localized SPR, which is only 100 or up to 500 nanometers per RIU. But the LSPR has other advantages in enhancing the electromagnetic field near the nanostructure. There is very high localization of the electromagnetic field, which causes enhancement of the spectroscopic signals like Raman and fluorescence. Of course, nanoparticles can go many other places, like in cells, what most of us have been doing, and to monitor, places where you cannot excite actually extended SPR. So to make it short, I accumulate many of the devices and concepts we have been developing to one slide. We have been improving this extended SPR approach in a variety of ways. First of all, you can excite it using a prism, what's called prism coupling, or grating, or waveguide, or fiber, and so on. We work mainly with the prism and grating coupling. And there, for example, we improved the figure of merit by adding a nanolayer of high index material like 10 nanometer of silicon. And we showed that you can get enhancement of factor 10 in the figure of merit. In the spectral mode, in the angular mode is less, but still also an improvement. Another concept where we can control the penetration depth of the electromagnetic field inside the medium. Usually, as you might know, with SPR, it's something like lambda over 2 or less. So it's good for detecting small bioentities. If you have large cell, for example, the field where it penetrates does not cover the whole cell. Or if you have more than one cell, then it might be problematic, might not show a monotonic signal with the concentration. So it's very important to tailor the penetration depth to the type of the bioentity that you want to detect. And with this concept where you have a stack of insulator, metal insulator, you can do that depending on the wavelength. Actually, suddenly the sensitivity of this structure becomes very high to the wavelength. So with the red you can get a few microns penetration, while with the green, you get only 200 or 300 nanometers. So with the same device, we can tune the penetration depth. And I will show you some of the results later. Other concepts here, the system type concept, where how you detect. So here, instead of scanning the wavelength, we scanning the angle, sorry, we use a fan of rays, basically like diverging or converging beam, but we do that in one dimension, in one plane, the incidence plane. So this way you improve the contrast, and then you can detect it with a camera. You don't need to do any scanning. And what you see a dark line on bright background, and you follow the shift of this dark line. So based on that, we detected, we demonstrated many things. This is an example of bisphenol A. There are many other detection of analytes. Another example is detecting the phase instead of looking at the intensity or the position of the tip, because the phase has a jump actually at the resonance, near the resonance. So when you have this large jump, you actually find you cannot really measure the phase directly. You measure a phase difference with some intensity, like interferometry, or in this case, we call it interferometry, common path interferometry, which is simply ellipsometry. In other words, because you have the two modes of the same beam, the TE and TM. The TE does not experience any resonance, but the TM does. So when you take the phase difference, or you can also measure at the same time what's called tangent psi, the ratio between the two, and we demonstrated that in a variety of ways. This one showing the use of liquid crystal device, actually giving three different phases. On these three phases, we can then find the ellipsometric parameters. With the grating coupling, we have a variety of concepts as well. One of them, which uses very thin metallic grating, like 20 nanometer thin, and the slits are very narrow. That's called extraordinary optical transmission, enhanced optical transmission. The phenomenon actually discovered first by Edison, but people have been using usually thick grating or thick array of nano holes, and you get very little transmission, like 1 or 3% at most. Here, by doing that very thin, you can get up to 30%, which is a big difference. And besides that, because it's thin enough, you excite two modes, actually, one on the bottom of the grating, one on the top. And because the one on the top can be far away from the analyte, you can close part of the spacing, for example, with oxide or something else, so that the field for this mode does not arrive to the analyte. So it becomes insensitive to the analyte refractive index, and you can use it as a reference. As you see here, this peak is not shifting, while all these are shifting with the change of the. So you have a reference measurement which can compensate for many instabilities, drifts, maybe temperature, and so on. Then we also did that with the electric grating on top of metal film. Again, the grating need to be very thin in order. We need it also simply in order to excite the SPR, and you use quite thin metal, thinner than the one usually used with the prism. So again, you can excite the two modes, one on the bottom, one on the top, and you can again do the self-reference measurement. Again, this has a very detailed properties. They are explained in this paper. You can use it in the wavelength and the angle or intensity mode and so on. Okay, I will switch. As mentioned, we have been working on this, developing a device which incorporates at least part of these methodologies that I mentioned. It's a very compact, like 5 centimeter height, and it has 2 channels. Now we increased the number of channels to 4. Last year or the year before, actually, we had this project during the Corona to develop it into a point of care device for COVID-19 virus, the coronavirus. And the idea was behind bringing it to more easy to use for us in a hospital or a clinic. We also developed this idea of incorporating a magnetic field, simply a motorized magnet, which can attract then magnetic nanoparticles. The idea is that to have the antibodies on the particle, which can catch the analyte, and then you will have also the antibodies on the surface, so they will catch the analyte, let's say, from the other side. When you apply a field, you bring the particles to the surface, and when you remove the field, if they are, you have some particles attached to the surface, they will remain there, and you will see it as a signal. The advantage of it that it will increase the now. Not even here. Yeah, so first of all, we increase the number of channels, and by the way, we are using a Turkish company in Ankara, microfluidics tool, to produce these PDMS channels, 4 channels now, and we can detect them simultaneously. These are done at different magnetic fields. You don't see the changes because the scale is not sensitive. When you increase the scale, you can see now the effect of the magnetic field at different concentrations. Here you can see that you can detect even something like 0.1 picogram per milliliter. You can see the difference. If you calculate how many particles you have, these are like 200 nanometer particles. How many you have in the interaction region with the plasmon, you will see that you get less than a particle. Which means
what are you detecting here? Viruses?
this is the SPR signal. So we got the translated into refractive index.
No, I mean, what are you detecting? I mean, the virus
No,
particles?
this is just the particles.
I see.
Okay, just the particles. So we wanted to show that we are actually very sensitive. Here you can detect a single particle. So if you are able to attach a single virus or single molecule even to a particle, it means you can detect single molecule, which is very nice.
250 nanometers.
Sorry?
The size of particles you're detecting is 250 nanometers.
250,
Yeah.
yeah, 250 or 200.
I see.
Okay. Okay. So I will switch to nanoplasmonic sensor now. And here we started our work with these types of nanostructured thin film made by optic angle deposition, where you get nanocolumns. They could be slanted. If you start rotating the substrate during deposition, you can get a variety of shapes like zigzags or helical and so on. we were the first to show that actually they can enhance the fluorescence. We investigated that variety of materials. As you can see here, both the spectroscopic signal and the image showing a luminescent bacteria on top of the substrate as compared to a standard silver film where you almost see nothing. Then we optimized them in terms of cells. And you can see here detection of monolayer of 4 ATP aminotiol molecule, where you see almost nothing on a reference. In this case, the reference is silver on silicon, and this is the nanorods. And with that, we did also a lot of detection bacteria, here a biomarker called endocrine disruptor. Sorry, it's called the vitellogenin protein, which is a biomarker for endocrine disruptors in water. If you have the EDCs in water, then the VG will appear in the shrimp, and means you are not allowed to eat the shrimp in this case, or to drink it, to use that water because it has endocrine disruptors. Okay. Then I thought that maybe we should combine the nano SPR with the extended SPR. Why? Because if you excite the localized SPR from free space, you will get some enhancement factor. If you get, let's say, take a sphere, you know it's something like times 40, 50, depending slightly on the radius. And on the other hand, if we excite the extended SPR, let's say on the surface of the metal film, we get also enhancement quite similar, like 10, 20, slightly maybe less. However, if we put the particle on top of the metal film, it means we get here concentration of the field, which will then excite the localized. So we expect to see a multiplication of the two factors. So we should see at least factor of 10. If we think about Raman scattering, which goes like the field and to the power 4, we should get much higher Raman enhancement. The same with the fluorescence. So when we did first of all, you can do that with other techniques, so other excitation techniques, like with the grating, and we did that with a waveguide or with a fiber. So when we did the simulation, we got here even much higher enhancement than we expected. It's exact simulation using the well-known packages like COMSOL, numerical, and you can see when you approach the angle, the resonance angle for the localized SPR, you suddenly see the field get enhanced a lot. And the width here of the enhancement peak is exactly the width of the extended SPR. So to look for it, you know where is the angle of the ESPR. Then you start varying either your wavelength or the size of the particle so that the two resonances match each other. You get strong coupling exactly at the resonance. The reason why we get larger enhancement, we think because of what's called mirror charge. When you have the particle on top of the metal film, you get a factor coming from the mirror charge. Then when we did the experiment using SIF and Raman, here you get something like 10 to the 10 enhancement factor. And here we got something like factor 70. There is an optimum on the distance between the particles, because if they are very dense, then they start to act like effectively like an additional layer of metal, which will deteriorate the whole even extended SPR as well. And if they are far away, then you will get less hot spots. So there must be some optimum. In this case, it's around 1 micron distance between the particles is about the optimum, and we showed that also experimentally by spinning a variety of concentrations and then measuring the distance with the scanning electron microscope. Okay, lately we went into a structure which is quite interesting. It's made by porous silicon, done with electrochemical etching, which when we deposit metal on top of it, you expect to see some enhancement of cells or fluorescence. And when we measure the reflection, cannot measure transmission because silicon is absorbing. So we see here a wide dip, which corresponds to the localized SPR, but then there is a small one here. So we think that because it's kind of microporous silicon, you have regions which are quite large, like 5 micron between the holes, and also it's slightly periodic, not completely random. To look, for example, in this direction is almost periodic, same here, and so on. So you expect to excite the localized SPR, let's see at the corners, at the edges. But then there is possibility that this LSPR will excite also the extended one, which will propagate on the continuous film between the holes. That's why you get this coupling. But when you have this coupling between the two, you see these two resonances, and that's called Rabi splitting, the phenomenon known from quantum mechanics. It happens once you have coupling between two oscillators. So when we did the experiment, we actually get a lot of enhancement here, something like 10 to the 7 estimated, and we get again an optimum at around 200 nanometer gold, because if you add more, it will become more like continuous structure. If you have less, it might not cover the whole area. So there is an optimum thickness. And with this, we tried to detect an explosive, partially supported by NATO project for explosives detection. In this case, picric acid is the easiest actually, and the safest one, because it's important when you want to purchase these materials. Sometimes you need to have the police coming with the material. So in this case, picric acid is relatively easy to purchase and easy to use. You can see here quite specific peak around 1360 or 36 actually, sorry, 1336, which grows linearly with the concentration of the solution, the picric acid solution. Another point here, in all these structures, including even periodic ones, you always have variability over the surface. When you measure Raman, you see variability. Simply, I think the reason is because you have very strong signal, is very sensitive to everything. So very small variations on the surface will also change the signal. So if you are relying on detecting the intensity, it is problematic if the intensity is changing. So that's why we investigated this, and we found that if we take a ratio between the peak that we want to measure and another peak that is not changing, like this one here is not sensitive to the analyte, we get better reliability. We still have some variability, but it improves. And I think there is still a point here with Raman scattering to investigate the variability over the surface to improve it. Because this is what limits the detection. In fact, I mean, if you look at this, I mean, you can get signal variations, you can see them within picomolar or sometimes even femtomolar. But that's if you measure only at the same point. If you move to another point, you will see that the signal varies. So you cannot rely and say that it's really femtomolar. it's more safe to say that it's actually nanomolar because of this variability. But Raman is very sensitive, and that's why you need to take care of the variability of the surface. Okay, how much time I have?
You have, I mean, 15 minutes,
Okay,
20 minutes.
yeah, I will try to do this within 15 minutes. So my other activity is about liquid crystal devices for photonic applications, or what's called non-display applications. We know that at the year 2000, there was an explosion in the display industry, display market. In particular with the LCDs, they become very mature and comparable to, competitive to other types of displays, the LEDs and the other types. So the idea is, you know, we have these materials which have very high electro-optic response, a mature technology where people worked since I was a undergraduate student. There was a lot of work on you know, how to improve the displays, even with the Texas Instruments, the small screens, and so on. And during these years, like almost more than 50 years, there was a lot of work on how to improve displays until they arrived to a position where they are in good position. Now you can have large screen, you can look almost from 180 degrees, from top, bottom, and so on. And they are fast enough. So the idea is, why not to look for applications in other fields? And there are applications like that. It started almost at the same time, even in the 90s, when optical telecom industry started. So liquid crystal switches, filters, polarization controllers became very important for this field. Then with the issue with the imaging, polarimetric, spectral imaging using tunable filters, for example, this is from a company called CRI, used to be, it was sold to a big spectroscopy company, I forget the name. And then there is also the SLM, the spatial light modulator, which is pixelated device. It's called LCOS, liquid crystal on silicon. And then you can control the phase of the wavefront at each pixel. So you can correct aberrations, you can do graphic imaging, and many, many other applications. There was interest also in liquid crystals for detecting cancer a long time ago, even in the 70s, by simply using polysteric liquid crystals, which are sensitive to the temperature. They show different colors as the temperature changes, like we can detect less than a degree variation. And some companies even producing them as thermometers, I think, and materials for detecting shorts in the semiconductor industry, like what's called in the back end. They coat the circuit with the material and see if there are color variations. It means there are some hotspots. There is also an interest in liquid crystals as biosensors. For example, here you have a virus inside. It will change the molecules orientation in that area. And therefore, if you have been between cross polarizers, in this case, it will get dark. But if you have variations, you will see light. So it's very sensitive in this sense, because you look at light in a dark background. And many, many other applications, even lasers, liquid crystal tunable lasers, robots, micro robots, goggles used to control the light, LCD projectors also incorporating these SLMs for projecting the image. You got the image from internet, let's say, and then it's actually translated into intensity variation. on the plane of the SLM, which you can then read it with external light and project it on the large screen. So that's the idea of the LCOS projector, which gives very high resolution because the resolution is determined by the pixel size. Okay, we have been working on a variety of concepts, as mentioned, polarization rotators, SLMs, special type of SLMs. Of course, there is no need to repeat what exists already in the industry. So in this case, it's an annular type SLM where you have circular electrodes, small number, but you can control, give a phase mask, what's called, to an imaging system and improve the resolution, the imaging depth. In this case, we went for application in the what's called road cameras. When the camera went to look at two cars at the same time, let's say distance is 5 meters or more, then one car will be defocused and difficult to read. So the idea is that now you can give a phase profile, if you might remember, for example, binary phase or quadratic phase, things like that. Means the phase will change in a binary way, like 0 pi, and so on, or in a quadratic way, like the radius to the power 3, you can get enhancement of the depth of field. What we did here is like combination of different phases, and then it gives you even more enhancement. In this case, we demonstrated that in the lab. And the idea is that once you have this image now, you can, with very simple processing, you can get it to the same limit like this one. Okay, I will move on because part of the other items here will be explained more in details. So this is a new concept for smart windows. We call it nano micro liquid crystals. The idea is to incorporate a nanoporous microparticles inside the liquid crystal. We started with nanoporous silicon particles. Then we tried that with organic nanocolloids. The idea is that it's a colloid, nanocolloids made of organic material like octadecanol, things like that. And the size of them will be on the micro scale. You need to have the size of the micro scale to have enough scattering. Otherwise, you will not see the scattering. There are another type of particles called cochlea. These are cigar-shaped particles. And by the way, here is a very nice example of collaboration between somebody like me who is not a chemist, not the organic chemist, not really producing organic particles, but these are from people who are producing them for drug delivery. As you might know, nanoporous particles are used for drug delivery. So, and by chance I know them, so okay, I said, send me a sample, and we incorporate it in the liquid crystal. We see the effect. At 0 voltage scattering, when you apply voltage, it becomes transparent. And here the nanocolloids, so this is the cochlea. The cochlea is like polypid layer, a sheet of polypid. Because it's a sheet, it folds, makes like a cigar sheet. This explains why we got this effect, why it is polarization independent. The whole issue about the liquid crystal smart windows, you don't need to use polarizers. Otherwise, you can do it with a standard device. So the idea here, if you look at the particle from 8 sides, like let's say it's a cube box, and then it's hydrophobic. The molecules will be arranged perpendicular to the surfaces. Then you look how the light, what is the refractive index seen by the light let's say light polarized along X, we'll see N parallel to the molecules here, but the Y polarization will see the N perpendicular. And so on, you will get that the number of, for each polarization, the number of regions where you get index mismatch is equal for the two polarizations, and that's why you get polarization. Okay, I worked also a lot on thermophobic materials as part of the project Mr. was aware of in Singapore. For the last 5 years, actually, we designed and built a variety of the nano oxide structures in order to improve its properties as a thermophobic window. And here the idea came to combine it because VO2 is a thermophobic material that's nice. It can control the transmission in the IR, so it can heat the house at cold days or cool it down or keep it cold at the hot days. It is 90 degrees, but in principle, the transition temperature is 68 degrees, and you can lower it by some other means, like doping, for example, with other material like tungsten. And you can see that the visible transmission is not changing. So you can still see through the window and use it to save you some energy of heating or cooling. That was the idea. But now what if we want to control also the visible? So the main point with liquid crystal device, the scattering device cannot control the amount of infrared radiation going to the house, because the scattering is relying on me-scattering. Me-scattering, when you have the wavelength comparable to the size of the particle, or maybe even slightly less. So me-scattering is forward scattering. The majority of the scattering goes inside the house, no matter what's the temperature. It doesn't matter the temperature or the voltage. It does not depend on the voltage. So you get, no matter what you do, what's called PDLC now, and many of the other techniques using scattering, like the suspending particle approach, some other, even the electrochromic materials, they rely on absorption. So still absorption means absorbed at the window, so part of the heat might go inside. So they are good for controlling the visible, controlling the transparency. So that was the idea, to incorporate it, to integrate it together with the liquid crystal layer. So the liquid crystal can control the visible. It also, doesn't control the changes. When you measure transmission, you see some changes, but you actually are not collecting the whole scattering amount of light. So this way you can both control the visible, the transparency, and the VO2 can control the infrared radiation. Okay. Now I will talk a little bit about devices incorporated into imaging, like a special device called tunable achromatic wave plate. As we know, if you go to buy a chromatic wave plate these days, they are made of two crystals, bulk crystals, like quartz, calcite, or some other materials. They combine it together at 90 degrees, the optic axis in favor of 90 degrees, so that the total retardation is the difference between the two. And if you have different dispersion, different thicknesses, you can get to a position where you have a constant retardation over quite wide range, usually like 200 nanometers or so. Now we thought about the idea that using two liquid crystal devices, and we can control the dispersion with the voltage. We know that retardation in a liquid crystal device is function of the wavelength, that's the dispersion. is function of the applied voltage. So it means if we take two devices, we apply different voltages, we can expect to see some compensation, two different voltages, maybe different materials, maybe different thicknesses as well. When we did it, we were surprised actually to see, first of all, this is a simulation. It shows the transmission between two polarizers. And for example, when it becomes 50% here, it means you have circular polarization. So the phase retardation is pi/2. When it's 100% between parallel polarizers, it will be 100% when you have 2 pi phase retardation. And so on. Between crossed polarizers, if it's 100%, it means you have pi. So you can switch between the three phases using the same device. But with the bulk crystal devices, you have only one retardation. And surprisingly, with different sets of voltages, you can also choose the range where it is automatic. So it's a very powerful device. Take this one. It shows the analysis how it works. So this is experimental result showing the switching between the three different levels, 0, pi, and pi/2. Now we try to, usually you need a quite thick device in order to have this compensation, like a few tens of microns. If you know something about liquid crystals, when they are thick, they become slow. So the idea is to make it faster. We know that metamaterials, when they are combined with liquid crystals, they can create faster devices, more smaller, miniature, and so on. So we went into this idea of using sub-wavelength grating, in this case made of silicon, simply etched on silicon, 800 nanometer high. And when you have the period is much less than the wavelength, we know that this grating start to behave like an isotropic plate, right? Because the period is very small, it only doesn't cause any diffraction. But you expect to have a refractive index along the lines different from the one perpendicular. So you have a form bifurcations. A well-known phenomenon when you have nanomaterials in general, if they are very nano, like they make the period on the range of 50 nanometers, the thickness becomes smaller, right? You will not see. But if you have order, like some periodicity, usually you still have this effect of bifurcations. Now, when we combine it, in this case, it's as wave plate for the infrared range, because we have the period is 350 nanometers, and the refractive index of silicon is quite high, so it's not good for the visible range, mainly for the 1500 nanometer range, which is good, because this is the range of optical communication. And when we combine it with the liquid crystals enough, first doing it with a simulation, we show that it's enough to use a single device, 8 micron thickness, and it works even very nicely. It shows a range of almost 700 nanometers in the infrared range. So it improved the speed a lot. I mean, if you think the ratio between the thicknesses to the power 2, that's like factor of 50, something like that. We combine this device into a camera and we try to do a lot of to demonstrate a variety of applications. even with a cell phone. And here are some of them. For example, in dermatology, you look at tissue. When you take pictures like this, you see nothing. Of course, you do the imaging, usually because it's scattering medium. You don't really image directly, otherwise you will see the surface. But you want to see something inside, that's the idea. So you irradiate at an angle and measure at normal incidence. You measure the scattered light. So when you look at the scattered light, you see something like this. But when you do that at the three different retardation levels, and the very simple algebra between them, you start to see structure in the space. And here the idea is to try, this is like a bare skin. So the idea was to try to estimate the bare depth, something that dermatologists would like to have, a tool like that, to be able to estimate the bare depth if skin is bare. This is showing some archaeological applications. You look at old coins. When you do that, the regular images you almost see nothing. With the using the retarder, you can see this biometry, and also looking from far away, right of objects. When you look at the polarimetric images, you start to see details not seen with the standard image. So that's polarimetric imaging. When you have the three different faces, you can also think about building ellipsometer. Simply by having three different faces, like pi, 2 pi, and pi over 2, you can extract what's called cosine delta, the phase difference between the TE and TM polarizations, and the ratio between them, tangent psi or sine 2 psi. So we demonstrated that on a surface plasmon resonance device by measuring the phase and also the ratio, the tangent psi or sine 2 psi. Sine 2 psi is like, tangent psi is actually the ratio between TM over TE. So it's like the SPR itself, with some additional properties, maybe slightly narrower. But the idea is that the phase here gives you the sharp jump. So when you look at cosine delta, you see the jump here, which means you can get a better detection. Okay. We played with a variety of configurations of liquid crystals to create tunable filters. This shows another interesting device using sub-wavelength grating combined with a waveguide. And with this structure called guided mode resonance, you can get a resonance on the reflectivity at certain wavelength. The idea is that using liquid crystal layer, you can tune it. It works, and then this shows the experimental result. The main point is that it can be fast because it's thin layer of liquid crystal. Tuning range is limited, something like 40 nanometers or 50 nanometers. It can be useful for optical communications, but if you want to do imaging, you need usually wider range. So we have been working also on improving the range, but when you improve the range, you also usually it comes on the expense of other things. Yeah. So in this case, we wanted few things. One is to make a fast device, fast tuning between different wavelengths. The other one to get high enough transmission, and also narrow peaks. So when you ask for these things, either you lose the transmission or you lose the speed. So the idea is to make a compromise, and the compromise here is to do it in a multispectral way. And the way we do it is by combining a passive filter combined with tunable device made of small number of devices. So the 9 peaks here, they are coming from a passive filter. And the wide one is the liquid crystal, so it's moving from one band to the other. And because now it's wide, it can be made from like 2 devices only. So it can be fast and gives you quite high transmission. As you can see, this is the experimental result. This you can think about it as tunable source, like connected, attach it to a fiber, and then tune the wavelength. You can use it for variety of applications. This shows some applications like food sensing, remote sensing, and so on. Then we also combine polarimetric and spectral imaging into this modeling for skin cancer detection. The idea is to take many images at different wavelengths, different polarizations, and apply algorithms. Then when you compare to the pathological results, you start to get a way to distinguish between cancer or normal. And this is one of the parameters. I think let's skip this one for some results. Those been, yeah, this is the second company until now is trying to commercialize this filter, combine with the camera, or the automatic wave plate combined with the camera. Thank you very much. I think, fortunately, this is Shakura.
Thank you very much, Professor Abdulhalim. This is, I mean, obviously you have a lot to tell.
Yeah.
I mean, there's too much to share.
Yeah.
It's unbelievable. So, any questions?
I have a question regarding using the liquid crystals with the vanadium.
The liquid crystal, what?
With the vanadium.
Yes.
Because the vanadium is not stable and changes its valence from 5 to 7. So how you make it possible to make an application?
Well, for now it's research. I mean, I agree that vanadium oxide very sensitive to oxide and so on. So we think actually by having the layer inside liquid crystal device, it's protected from oxygen. So it might work better in this sense. It might stay for a longer time.
So isn't it not possible to replace it with another oxide? One of you maybe on the periodic table, you know, around the.
There are others like tungsten oxide, nickel, they're all thermophobic, but the vanadium has the lowest temperature. The best. The others maybe need few other degrees.
The question about liquid crystal. So currently, the smart meters that are available in the market requires power supply to remain transparent, and the opposite. So you turn it off and it becomes opaque. Is there a material that can be already transparent without power and then turn opaque when you apply voltage?
Yeah, actually, we just demonstrated. I didn't show that. It's possible, just aligning the liquid crystal. Use liquid crystal delta epsilon, the electrical negative, align it perpendicular, so at 0 voltage you will get transparent, when you apply voltage becomes scattered. So that's another improvement. The best will be to make it bistable, which means you memory. So you apply voltage, turn it off, it will stay at that position, and then you bring it to the other state, turn the voltage off, it will remain in that state. We didn't try this. Yes, there are different possibilities. With PDLC, people have been.
Any other questions? I have one. So, because this is about sensing, of course.
Yeah.
So, how do you deal with the because all these sensors, SPR and source, they are sensitive to metrics. I mean, because whatever is, if you're trying to detect something in why are you going to do that? I mean, are you planning to do some kind of separation before sensing it, or just, for example, bacteria? Is it, can you just take some sample and try? Of course, not easy, but I mean, is it possible to, for example, detect an analyte and its image in natural metrics?
I mean, we used specific binding diagram for the bacteria. We used bacteria fast before bacteria fast. That's a lot of and some, the others also. We always have some receptor.
I see.
If we wanted to show specificity.
Also, you need to do washing, to
Yeah.
remove the vitamins, stuff.
It's not me, usually somebody.
I see.
More
But usually it's
familiar.
metal surfaces. I mean, any surface that scale, this. all
Yeah,
these
silver,
materials, they stick.
actually, silver is sensitive. I mean, it can oxidize quickly and so on, but with the nanostructures, we were surprised that even after 1 year. Gold, of course, is more stable.
So if you don't even, yeah, I think we have one question.
We tried any blending with other materials, liquid crystals with other materials or composites.
What materials? Analyze.
For example, organic materials. Did you use inorganic materials? Polymers, for example.
Mix one.
It's liquid crystals.
To increase the performances. To increase the performances.
Of
Which
liquid
device?
crystals.
The one with the film. The one with the film. I don't remember. Not the smart window. There was a film. If I'm not mistaken. There was a. I thought it's polymer. Was it polymer or they are all inorganic type? It is a roll like this. Roll back to the.
Yeah, we can practice it back.
Hocam, siz kristal, liquid kristalden bahsediyorsunuz.
Which one? These are not ships.
Burada bir yerde.
This one?
No.
Yeah, this one.
I think the polymer or
We have the liquid crystal.
only
Well, you need to align it. So you use a polymer layer on the top of the circuit. This is like 30 to 50 nanometer layer. We do rubbing, so mechanical rubbing, to align the liquid crystal. Then we use the particles, could be organic, could be non-organic.
One last question. How did you manage to capture, for example, bacteria on the surface of the SPR enhancement magnetic nanoparticle biosensor application for the photonic biosensor? I mean,
Capturing.
what was the
Bacteria?
effect for capturing? I mean, did you
We use
functionalize the surface or
Before bacteria.
only bacteriophage?
Yeah. I mean, before the bacteriophage, there is, I think, 4 ATP. And the whole process, you know, in UA and
Yeah,
I
I
can
mean,
show,
there
I
are
can
many
send
ways
you the
of doing
paper.
it.
Oh, okay.
They are
Yeah,
using it.
that would be
Yes,
great.
we have the full
Capture or
protocol.
antibody or microphage
Yeah.
or something like that
Yeah,
to capture.
yeah.
the-
You need to fill the sites which are not, that's, when you put the receptor, it doesn't necessarily fill the whole surface.
Oh, okay.
So you have that material which fills at least once
Okay.
and makes the sensor more reliable.
So if there is no further questions, let's thank Professor Abdulhalim one more
Thank you.
time. Thank you.